Good morning, everyone. Thank you for coming here. I'm going to be talking about connectivity and IIoT options. And there's a difference between industrial Internet of Things and Internet of Things, and I'll be teaching you about that today. Who is MultiTech? Well, my name is Dave Smith, and I'm the Senior Vice President of Engineering and Innovation at MultiTech. MultiTech has a company that's been in business for about 45 years. We're based in Minnesota. We're a manufacturer of a wide array of connectivity options, including M2M services, cellular services, and IoT services and products. We are a US-based engineering firm. We offer not only our standard products that you can buy and customize, but we also offer value-added services such as forward and reverse logistics, custom engineering, especially through our sister company, which is Connected Development. Well, they will do a full custom design for you that we can then turn around and manufacture for you. We are a top 100 M2M company, and we're working to be a top 100 IoT company as well. So let's talk about technology, because that's what I'm interested in. We have different kind of challenges when you're trying to connect IoT devices. And what's interesting is these challenges are pretty common across different use cases, across different industries and markets and things like that. And they're very difficult to balance, and every solution is a balance of these challenges. Some of them, or most of them, require battery operation for endpoints. You want them to be reliable, and you can go down this list. Harsh environments, long range, scalable, full duplex, all these different things. And how do you balance all these different requirements? Well, the answer is basically you can't with any given solution. From our experience in a wide variety of markets, most IoT solutions require more than one technology. And there are three general ones today in the wireless area that we use to pull to make our solutions in IoT markets. You have your LAN devices. That's Zigbee, Wi-Fi, Bluetooth. We're all familiar with that. They're nice. They have really high bandwidth, but they have short range, and they're not very good for battery life. So if you have tiny little devices that you want to go a long distance or get through a building or something like that, Wi-Fi isn't so good, or Bluetooth or Zigbee. But then we have the cellular side, and you can add satellite to that too, but that's far less common. Cellular is much more of a wide bandwidth and a longer range technology, and it's great. It's pretty much ubiquitous. It's around pretty much wherever you're going to go. But the problem with cellular is that it doesn't really do well with batteries. And you have this recurring monthly subscription cost generally associated with it. So most business models in the IoT world can't really handle subscription-based, or what we call operational expenses. And then you have low power WANs on the right side, where you're trading off this high bandwidth for much longer range and longer battery life. And those are really good for little end devices that want to send little bits of data frequently or infrequently, but hopefully more infrequently than frequently. So these are the three categories of wireless connectivity options that you use to pull from when you make IoT solutions. So here's where we want to talk about IoT versus industrial IoT. Okay? Completely different markets. They have completely different focus. In the IoT world, it's generally about a high volume, low cost product. Think of a Fitbit. Okay? The interesting thing about a Fitbit is they are all the same. Right? You don't buy a Fitbit and put your own software on it. Right? It's a one size fits all. They're identical. And the thing about IoT devices generally is they often have frequent interaction with people. Again, think of your Fitbit. You wear it on your arm. And that means, though, that it's probably not going to be in a very harsh environment, because people don't generally go into harsh environments, right? In addition to that, you're all familiar with commercial products. They have very short product life cycles. Apple replaces their products once a year, right, if you're lucky. If you try and go a cellular dongle from Verizon, try and buy one of those can change as frequently as every 3 months. So if you're trying to supply a product that you can deliver over a period of years, it's very difficult to do. And in addition, this is another key characteristic of IoT devices, is they share their data broadly. Again, imagine your Fitbit. Your Fitbit's going to connect to your phone. It's going to have maybe a Fitbit app. There's a health app on your phone. You're going to forward that data out into the cloud, and perhaps share it with the Fitbit cloud, but you might also share it with your personal trainer, and you can all see that I have one, or your doctor, right? If you're trying to monitor your heart rate, things like that. So this data is often shared broadly with IoT devices. Now contrast that with industrial IoT. The number one thing I'm sure you've all heard in the industrial side is security, right? High reliability. And part of security is controlling where the data goes, right? Not letting anybody get to it. And another big thing with industrial IoT is managing end devices, because they're often put in harsh environments where people don't go. They don't have a lot of interaction with people. Imagine a little control on top of a streetlight. People aren't often going to be climbing up there to touch this thing, do anything with it. So you need to have a remote way to manage it and maintain it and all that. And it has to be able to be deployed and sit there for years, outdoors. In addition to that, you have to have a long product life cycle. Let's take the streetlight example again. There's a lot of streetlights in the country, right? If we start today and we want to wire up every streetlight in the country, it's going to take a few years. And during that time, they're going to put out more streetlights because there's development going on. And then once you get that done, you haven't made any money or saved any money or done anything really, right? So you need to have an operational life on this thing that's going to have to be for years to make up your investment. So that whole life cycle could be a decade, maybe 2 decades. And all during that time, you're going to have lightning strikes, you're going to have cars knocking down light posts and things like that. You're going to have to replace these things, and they have to be identical. So you can have a consistent business model, a consistent cost model. So you have to have a very long product life cycle. In addition to this, you also have data that is not widely shared. It is often sent to only 1 or maybe 2 different places, and is relatively jealously guarded for one reason or another. Pick streetlights again. You don't want a hacker to be able to shut the streetlights off at the wrong time, and people maybe get in car accidents, or pedestrians get hit because they're not seen. So you want to tightly control where the data goes and how it's used. So that's industrial IoT versus regular IoT. So let's talk about LPWAN technologies. First of all, you've heard the term LPWAN, right? It's a generic term, it's an umbrella term, and it really refers to 4 characteristics. It doesn't refer to a particular technology, it refers to 4 characteristics of that technology. One is long range. The second is long battery life. And then there's low cost, right? And low bit rate. So you can kind of think of long, long, low, low, right? These are the 4 characteristics of an LPWAN. Now contrast that with cellular. Well, cellular might not hit the low cost, they're not going to hit the low battery life. But they probably hit the wide area, you know, relatively speaking. And the data rate, well, they have much higher data rate. So this is unique to LPWAN. So when people use that phrase or that word, this is what they're referring to. So how do this LPWAN and specifically LTE or cellular technologies, how do they interact, right? Because these are overlapping markets. And what you found is broadband cellular, for a number of years now, has enjoyed kind of a monopoly because they were really the only ubiquitous network that you could connect to easily and send data through. I mean, LPWAN is fairly new. And so it dominated most of these vertical markets here for a while. In 2016, there's been a large acceleration of LPWAN applications. And what you can see, if you look at the trend there in 2019, it just means that in those particular verticals, it's really hard for an LPWAN to address a market. I mean, when you're talking about, you know, smartphones, tablets, and gateways, people are going to want to watch video, for example. And LPWANs have a low bit rate, so they're not going to support that. So there's 3 different kinds of LPWAN networks, okay? We talk about all 3 of these, and MultiTech was one of the first to identify the enterprise one, so I'll explain that one. in a minute. But the first one that most people think of is public. And that's where you have a carrier, and you can pick them like AT&T, Verizon. But actually in Europe, there are a bunch of smaller companies that are taking the role of carriers like Actility, Orbitwise, KPN, Swisscom. They're a real carrier though. And what do? They provide a network. And you would buy an endpoint and connect it to their network. So what's good about that is you have a low capital expenditure up front because all you're buying are endpoints. You don't have to create a network, you don't have to set anything up. But you trade that off for higher operational expense in the future because every month you're going to pay for each device to use their network. And for many people, network management, or being able to control the network and decide where a network is, right? Because you may want to put an endpoint in a spot, but the carrier doesn't have coverage there, you're out of luck. But you can usually do mobility, although NB-IoT, I'll talk about that later, is not really good for mobility at all. It doesn't really work. But generally, you can move things around, and you can get things out very quickly. So that's what's really good about the public network. Let's flip over to the private side, the opposite end. Private networks are, let's say you have a business, and you want to, monitor your freezer and your fresh food area, or something if it's a grocery store, or you want to monitor something else, and it's really geographically constrained, maybe one building, maybe a small area, and you want that data for your own uses. So you set up a private network. That way, you don't have to pay the operational expense every month. Saves you that. You do have a little bit more capital expense up front to buy a gateway or a router and set up your own network. But you do enjoy the ability to control your own network as well. And the key thing with that is your data never leaves your hands. So if you don't want others to see your data, you set up a private network. So the middle one is the one that we're seeing a lot of growth in. Probably, well, the vast majority of the customer contacts we come into right now are enterprise level networks. So what is an enterprise level network? It's a large private network, essentially. Imagine a large company that might be geographically distributed or have multiple locations. They want to get data from these locations and aggregate them up into their own systems for their own uses, right? Imagine McDonald's, and you want to have little networks at each McDonald's spot that tells you all sorts of stuff and aggregates it up to the corporate headquarters. And you don't want that data leaving your hands because it could be misused, right? It could be used against you in some companies. So you use an enterprise network. Well, the great thing about that is you have low operational expense because you own the network. And your network management is awesome because you put the network wherever you want it to be. So you already know that wherever you have stuff, it's going to be covered and you can get that data. It's not so good for your operational or your capital expense because you're going to have to create the whole network yourself and you're going to have to manage and maintain it, right? So you've got a little bit more capital expense up front. But you also completely own the data. It never leaves your network. So think about what we talked about, IoT and industrial IoT. Industrial IoT is more of the enterprise private side. IoT is more about the public side. Now, what we find is we have the public operators today. They recognize this, believe me, especially in Europe. And they're fighting a battle now between enterprise and public. And their approach is, we give you the security that you want and need, and we can't touch your data, and that's what they try and talk about. But at the end of the day, for a company that really wants to own and maintain, they don't want to take that chance. They want to own the whole thing. It's that important to them. So they want an enterprise network. So this is what you're going to see out in the market today. So this is actually a really cool slide, and I can say this because I didn't make it. Daniel Kwan made this, okay? We've updated it several times, but it's really good, and you should get a copy of this and keep it with you, because people often ask details that you can get off the slide, and by answering that question, you can get to the real questions, but they often think that all the most important stuff is on the slide. What we have here is we have on the left 3 columns are 3 LPWANs, and on the right 3 columns are the corresponding LTE or cellular technologies. Now, I know it's kind of hard to see. That's okay. That's why I said we'll get you copies. But what I can show you is they all have similar, the top parts are all very similar in terms of data rates and battery life and things like that. Okay? They're all, within a few points, dB or volts or whatever, of being the same. They all work very much the same. But the interesting thing is LoRa, the reason why it's in green, all the rest of those are public networks. Public network only. So if you want to do a private or an enterprise network, Sigfox, you can't do that. And with LTE, you can't do that. Ingenue will try and tell you you can, but they have to do it all for you. So, and then they manage and maintain it. So how is that different than a public network? I'm not sure. But here's some other things too. LoRa is the only one that allows you to do mobility. LTE Cat 1 and Cat M, yes, but they aren't really LPWAN. We included them there to be nice and to give you some additional information, but it's really NB-IoT that is the LPWAN competitor. And NB-IoT, you can't move around. When your device connects to a tower, it's like, imagine a dog with a chain to his doghouse, right? You can walk all around that doghouse, and as long as that device is still within talking range of that tower, yes, it can move around. But as soon as you go out of range of that tower, the device has to stop, and it has to look around and try and find another tower and then go through a join process and then start talking again. So it is not like when you're driving down the highway with your cell phone and you're having a conversation, and what you don't know is you're being passed from tower to tower to tower. You can't even tell on your phone call. It's not like that with NB-IoT. In addition to that, Ingenue is especially sensitive to being moved around. The way their technology works is it has to have a really tight phase lock on a signal. And so if I'm moving this fast, it's going to lose lock. So you can't even put it on a dog and track the dog. It'll lose lock. And this is even when it's within range of the same gateway. So these devices really can't move. In addition to that is location. The other key thing that the other ones don't do. You're going to have your traditional, I'm talking to this tower in cellular, right? And get that big blue circle on your map of where you could be. But all the rest of them, they don't support location-based services at all. Unless you go to a third-party provider and you mix it with Wi-Fi, right? If you're all familiar with LBS, you might not be. So a lot of times you can use local Wi-Fi networks, and you use a cloud-based service that will kind of sort of tell you where you are. It's called location-based services. You would have to use those and get a kind of sort of where you are answer. Whereas with LoRa, right now, directly off of the LoRa signal, and not using GPS or anything like that, the idea of locating an endpoint is definitely been done, and they're improving the accuracy. Today, the accuracy is about 100 to 200 meters, which is good enough to say I'm in the lake or I'm on dry land kind of thing. And for many applications, believe it or not, that's totally cool. For example, consider agriculture, and you just want something one on each acre. Okay, that's good enough. So the accuracy is being improved right now, and the goal is to get down to about 10 meters. I'm not sure that's going to happen anytime soon, but a few tens of meters I think will happen yet in 2017. But that's the only technology that will support that. So let's talk about LoRaWAN specific now. When people say LoRa, they're going to mean one of three things. I mean, I hear this all the time at the LoRa Alliance. People will say LoRa, and the context will tell you whether it's the LoRa radio, which is the LPWAN radio itself, or are they talking about the LoRaWAN protocol, which sits on top of it, or are they talking about the backend, which has a bunch of different cloud entities that you use to provide a more sophisticated network. A carrier would use these to provide public services, and enterprise would use these to set up their own network. So LoRa is just like that prior slide, and I don't know if you can see all the details, but basically it's a radio, and I'll go into how it works in the next few slides, that gives you really long range at fairly low bit rates and low battery usage. So it's a pure LPWAN radio. Doesn't pretend to be anything else. On top of that, we've created at the LoRa Alliance a thing called the LoRaWAN protocol. And what it does is it takes this radio and it allows you to structure information or data to be sent and received and to manage that channel, that communications channel from a network device. And that's what's called the network server. So conceptually, the LoRaWAN protocol connects the endpoint to the network server. That's all it does. And so this network server is this entity. It can actually be anywhere. It's on the network. So we put it in our conduit. We allow you to make a private network with a network server in the conduit, or we can put it up in the cloud. In either case, it is managing this communication channel with the endpoints. There's some other entities in the cloud as well. There's the join server. Join server is the entity or the element that is asked when a device wants to join a network. It is asked to do two things. To say, yes, you can. And it uses information from carriers to decide if you really do have an account, and you've been paying your bill, and we haven't shut you off, that kind of thing. And once it does that, once it says yes or no, it generates security keys. And I'll be getting into security a little bit later here, because I'm sure that you don't really know exactly how it works. And I can say this with certainty because we just changed it last week at the technical committee. And then on top of that, you have an application dispatch server. An application dispatch server is just simply something that says, hey, when an endpoint sends application data, it actually encrypts it separately and differently than a network packet. And technically, the network can't tell at all what is in the application data packet, which is good, right? That's why carriers are making public networks out of it. And that encrypted application packet is sent to the application dispatch server, which decrypts it and then hands it over to your application unencrypted or decrypted. And so if you were sending location data and you wanted it to go to Google Maps, that would decrypt it and pass it to Google Maps. And then you have the location server, as I mentioned, for location services. That's actually an entity in the cloud, and I'll describe a little bit later how location works. And then your applications sit all on top of that. So this is LoRa, depending on the context of the conversation. So at the lowest level, let's start the radio, okay? LoRa is actually a fairly old technology. In fact, it is so old that all the original patents have expired. Kind of came out of the military and intelligence services, where they wanted to be able to communicate over a long range, reliably, and not be listened into, right? So what did they come up with? They came up with a signal it's called Chirp. Chirp is just a way of modulating a signal in bursts without having a carrier wave. So let me back up a second here. Prior to this, it used to be when you had a radio communication, you would tune your radio to a carrier wave, right? And both sides one side would be transmitting, the other would be listening and lock onto this wave. And it would be very much like making a phone call where you're dialing and then you connect. And then once you've locked on, you could talk back and forth. And that was carrier wave-based technology. So prior to LoRa and Chirp especially, that's what you used. Well, that means though that if you're trying to see if someone's communicating, you can just scan the frequencies, right? Oh, look, there's a carrier wave, and then listen in. So how do you get around that? Well, you have this Chirp thing, which is non-carrier wave based. What it does is it sends preamble, it sends the beginning of a packet that you can be listening for and then lock onto it when you see it. So that's what the Chirp part is. You basically just start talking and you add some stuff on the front that allows a receiver to lock on and connect to you. So you don't have to be always locked onto each other. And then the spread spectrum is, when you take a signal, there's a couple of ways that you're going to see in industry that they use radios. And one is this narrowband. So you've heard of FSK or GFSK, all these current 802.15.4 radios, if you've ever heard those phrases, like all the TI radios and all these such things, they all work on narrowband operations. What they do is they take all the energy that they're using to transmit their signal and they squeeze it into a very narrow section, right? And the whole point of doing that is to get it above the noise floor. Have you all heard the term signal to noise ratio? SNR, okay? So signal to noise ratio means how much headroom do you have above the background noise, right, in order to hear a signal. This is a very simple concept. But with the FSK, GFSK, and all the excess FSK or K things, they require a signal that is above the noise floor. Otherwise, you're not going to hear anything. I'll give you an example. You're sitting across the table of someone in a restaurant, and you're talking. There's more and more people start coming in the restaurant, the noise level goes up, right? And it gets a little harder to hear, but you can still hear it, you keep talking, but more and more people show up, until finally the background noise is so loud that you can see the other person talking, you can't hear them. That's a signal to noise ratio of 0. You've now had the background noise reach the signal, and you can't tell. The way LoRa does it, because it's a spread spectrum, you can actually demodulate the signal below the noise floor. And what that would mean in that case would be, you'd be able to read the person's lips and still be able to communicate. And it might only be until someone actually gets and stands in between you. It gets so crowded that you can't see them the whole time, and then you start losing your communication. So that's what the digital spread spectrum does for you. It's very robust to interference. And I'll have a slide, I think the next slide talks about that. There's also another interesting thing about LoRa. The way it is encoded, the way we modulate the signal, is there's several different factors. And one of those factors is a thing called spreading factor. At this level, what it allows you to do is use the same frequency, but transmit 2 different things at the same time and not interfere with each other. That's a very useful thing, right? We have several different spreading factors, so for any given channel, if you use a different spreading factor, you can have multiple transmissions going on at once, and they don't interfere with each other. So this one, you're going to have to either read it or keep up with me. There's several key properties from LoRa that you're going to see that are highly competitive with other sorts of LPWAN technologies and other technologies. High robustness. I'm not going to read all that, but basically what happens is it's very resistant to interference from other sources. It's very resistant. If I can give you a little example. While I'm talking here, I'm making noise. This isn't interfering, but you can still tell what I'm saying, right? That's because how I'm talking is spread out, and my data rate is much lower than the frequency I was pounding on the table. So you could easily pick that out. Did anybody have difficulty understanding what I was saying? No. And that's why LoRa, being a digital spread spectrum system, when you get other interferers, which are generally like those narrowband FSK radios, it's like pounding on a table. Each one of those packets going by is like one hit on the table. And so we can we could talk all day long and not really be affected too much by interference. Another one is multipath and fading resistant. Now, you've all stood at a train stop and heard a train coming, right, or a siren, right? And a siren sounds different as it's coming up, and then when it's in front of you, and then it seems to change as it goes by. That's Doppler effect, or fading, okay? Technologies like Ingenue and RPMA, extremely susceptible to Doppler effect, to where just a few meters per second of motion will completely make them unable to talk. That's why Ingenue is not good for mobile applications. LoRa modulation is extremely not susceptible. It's extremely resistant to Doppler and fading. The way the modulation is done, the way you receive the modulation, there's a wide band of shifting that they can tolerate that keeps it so that if the device is moving towards you away, you don't really care. And then multipath, you're all familiar with the multipath term. Multipath is when an endpoint sends out a signal, but because of other objects or other reflections or other things in the environment, the receiver will seem to get echoes, maybe, you might want to call them echoes, signals that take longer to get there. So between you and me, right, I can talk and you can hear my voice is coming right at you, but what you may not be able to tell is that my voice is also bouncing off the walls and the ceiling and the back wall, so you're actually getting about 6 different versions of my voice. But your brain just locks on to the primary one and you understand what I'm saying, right? Similar thing with LoRa. Long range. Well, we all know that LoRa can transmit pretty far. I was talking with our chairman of the technical committee, and I think the record for LoRa was something like 1,800 miles at 14 dBm. But again, it was another one of these weather balloon sort of things. So the guy, and actually what got them was curvature of the Earth, ended up blocking the signal. But there was a guy in the UK, and he had a balloon with one endpoint, and he had another one, and he got down to, there's certain islands way down south. I have to remember now what those were, but anyway, it's really far. And that's because, it's pretty much line of sight. Nothing's in the middle, right? Nothing's to block, no interferers at that level. So not a real world sort of thing. Although there have been customers that do plan to put gateways in balloons and cycle them using weather patterns, but generally not a common use case, but it's a long way. Enhanced network capacity, I mentioned how you can have spreading factors allowing you to reuse channels. So LoRa modulation is what you would say spectrally efficient. It allows you to accurately use your spectrum that you've assigned it and get a lot of use. Now, one of the things you're going to hear just lately in the last few months is you're going to hear people saying, hey, wait a minute, LoRa is horrible for capacity because it's an Aloha network. And the Aloha network came out of some of the original networking stuff done years and years ago in Hawaii. An Aloha network is basically a bunch of things that want to talk that talk whenever they want to, right? So without waiting to see if the channel is free or anything like that. If I need to talk, I talk. And the theoretical max capacity of that kind of network is 18% of the available bandwidth. So people are saying, hey, LoRa is an Aloha network, and so all you're ever going to get is 18% possible of your total bit rate available. And the answer is, today, yes, that's kind of true. Except what's happening is there are other factors that make that argument not quite right. One of the factors is that LoRaWAN has an automatic data rate function. So it controls endpoints and the channel that they use and how they talk to allow more people to talk than you would normally have in a regular LoRa network. In addition to that, there's not an equal distribution of data rates in any given LoRa network. So what happens is most endpoints will talk at data rate 7, which is the fastest data rate. And it's only if you can't get through at that rate that it starts dropping you down to a slower data rate. And so the net result of all this is you get more than 18% capacity. Different models will give you different numbers, but you get significantly more than a LoRa network. So if you hear this from customers, they say, oh, it's a LoRa network, it's 18%. You say, not really, okay? Ranging localization, I talked about that also on the prior slide. One of the things from LoRa is that we can do ranging, which is just simply how far away from me is that endpoint, and then localization, which is exactly where is that endpoint. The difference between the two is ranging is concerned with one gateway. Localization usually requires multiple gateways to triangulate. So LoRa bandwidths are very important because they allow you to use your spectrum more efficiently. They give you a variety of data rates and things like that. So in the LoRa bandwidths that we use, we're using the 1272 in our endpoint. We also have products coming out with the 1276. So the 1276 is a different one, and I won't talk about that one today. I'll just talk about the 1272. 1272 has 3 different bandwidths, 125, 250, and 500 kilohertz. So whenever it talks, it will use a channel that either uses one of those 3. In LoRaWAN, the protocol, it makes use of all those radio capabilities in Europe. In the US, we only use the 125 and 500. And I'm not sure exactly why, other than the fact that we had so much more spectrum here, that we have so many more channels that we don't really need the 250. But it's open for improvement, and we may be adding that in the future. But today, it's 125 and 500 kilohertz. And then it says each bandwidth supports multiple data rates. So there's this term that's called data rate. Data rate is a combination of 2 things, okay? You've heard me mention spreading factor, and then you have the bandwidth. So the combination of spreading factor and bandwidth gives you a thing called a data rate. A data rate is just how many bits per second are you transmitting or receiving, right? I'm transmitting at 5,000 bits per second or 50,000 bits per second. So the data rate comes from the spreading factor and the bandwidth. So bandwidth, I'll start with that one, that's easy. How much of a frequency chunk do you use when you use your channel, right? How wide, what piece of spectrum do you use? So that's the 125, the 250, or the 500. In the US, it's 125 or 500. Now, the spreading factor is a little different. Remember, this is a spread spectrum radio. So it'll take everything we call a symbol, think of it like a byte, and it spreads it out over the frequency range. And this spreading factor is how many, the symbol of one of the things, is it gets broken down into little pieces. They're called chips, okay? So each chip, take the whole set of chips from a symbol, that gives you a symbol. The number of chips you break a symbol down into is determined by the spreading factor. And it's a lot because it's 2 to the spreading factor number pieces. So if you have a spreading factor, we don't generally use 6. The radio has that capability, but not LoRaWAN protocol, we don't use that. So a spreading factor of 7. 2 to the 7 is 128, right? So it's going to take every symbol and it's going to break it up into 128 chips, right? Now if you have a spreading factor of 12, it's going to take every symbol and break it into 4,096 chips. And that's why the higher the spreading factor, the lower the effective data rate, because you're sending more chips per symbol, right? Now you want to send, hello world, right, as a number of characters, I don't know, whatever it is, 10, whatever, 12, and you're going to break each one of those bytes into 128 chips that you send or 4,096 chips that you send, it's going to take longer to send the 4,096 times the number of bytes than it will to send the 128 times the number of bytes. That's why your effective data rate is lower. But the higher the data rate, the better your sensitivity. So you're always trading off. You're trading off your bit rate for how far you can go, your sensitivity, or how well you can penetrate a building. And that's why we use a thing called automatic data rate in the LoRaWAN protocol to say, look, we always want to have the highest bit rate we can, but if you can't operate it reliably at a spreading factor of 7 and a certain bandwidth, we'll adjust that to where we can have a reliable signal, and then that's the data rate. So the data rate comes from the spreading factor and the bandwidth. So in that right-hand part there, you see a bandwidth of 125 kilohertz at the top, a spreading factor of 6. You're going to have a data rate of 9,000 bits per second. It's pretty good. That's actually really good compared to, say, Sigfox, right? Or at the other end, if you have the same thing, the next one down, same bandwidth, but a spreading factor of 12, now you're down to under 300 bits per second, which is about the same as Sigfox, right? So you can see the effect of the spreading factor. And then if you look at the same thing at the bottom using the 500 kilohertz channel, you're going to see that 9 kilobits per second goes up to about 37 kilobits per second. So the bandwidth, the extra bandwidth, gives you more capacity, right? So this, we've tried to make this simple in the LoRaWAN and kind of hide this spreading factor bandwidth, relatively confusing thing under a thing called a data rate. And in the LoRaWAN protocol, there are specified data rates. I'm going to work at this many bits per second. And if you know that, you know what your spreading factor needs to be, and you know what your bandwidth needs to be. Have I confused you all sufficiently? I can make it more confusing. Okay. In addition to that, there's a forward error correction code built in to the system. Now, LoRaWAN only uses one of them, the 4.5. But basically, what this allows the radio to do is it's a Hamming code very similar to memory error codes. So if you're familiar with memory devices, where you'll have your memory value and then an error code field with it, right? And you can tell if any of the bits are wrong. And with some codes, you can actually correct single bit errors and things like that. But it's a very similar approach used here with LoRa. So part of the reason why the data rate is low, in addition to the spreading factors and all that, is that we're also sending an error correcting code with it so that we can recover from bit errors. This helps make the communication channel more reliable and more robust. We only use one of the 4 available, but for custom applications, where you expect a lot of bit errors, you can use different ones. But so far, we haven't seen anything that really needs anything more than the 4.5. So number coexistence. This is something I talked about earlier when I was pounding the table. Okay, the LoRa signal is a very long period signal, right? And so when you get interference from other kinds of radios, it's okay, because you're getting still most of the signal. And you're also able to use the error correcting code to recover anything that was really squished, right? So you still get a very robust communications capability in the case of other channels getting in your way, other systems getting in your way. So what does that mean, though, to your customers? Well, what that means is that we're using the ISM bands, and those are free, and anybody can use them. And so when you use LoRa in the ISM band, other people who are not using LoRa are interfering with each other and not being very happy about it. Oil and gas industry is a big problem because they're all using FSK radios. And those really just, they bounce off all the metal and they go nuts. You put a LoRa radio system in that environment, it works great, because the other systems don't even see LoRa. To them, LoRa looks like noise. So the only thing that someone with an existing FSK radio is going to see is they're going to see what appears to be the noise floor went up a little bit. That's all. They won't even hardly tell you're there. Whereas with LoRa, all this existing traffic, we're going to pretty much work as normal. It's not going to be a problem. And so this coexistence is extremely important for certain industries where we're trying to get LoRa adopted, like oil and gas, where there's a long-term existing approach, such as FSK in the oil and gas industry, that might otherwise be an issue. Turns out it's not really. So here's a couple of examples. I don't know how familiar you are with a company called Senet. Dave Chendall is their CTO. He's a great guy. He provided me this. Senet does, among other things, they're creating themselves a coast-to-coast public network for LoRa. That's their goal. And they service various vertical markets. One of the vertical markets they service is tank monitoring. So this is an example from California, kind of the northern part of California, just south of San Francisco, Silicon Valley kind of area. And what happens is they put a gateway on top of Mount Oso. So it's kind of high, it's up there. And what it does is it's looking down into the valley, and all those little pins are tanks that they're monitoring, and they just have an endpoint at each tank. This is if it's full or empty. Well, the interesting thing about this is this green half circle, that's a 25-mile radius circle. So these little endpoints from 25 miles away, reliably communicating, no problem whatsoever. It's interesting though is his farthest node, the farthest point, is 94 miles away. Now in talking with Dave, they don't get, I think these endpoints every day they send a reading, something like that. And I think this one from 94 miles away, he only gets a couple of readings a week. But it's more than enough to tell if the tank is empty or full, right? And they just are a little more careful at looking at its trends. But 94 miles from one gateway, that's pretty good. Another example is there was a trial done in Tokyo. Now, I'm not super familiar with Tokyo. I've actually been there once. But it struck me as being very dense, right? Very, very compact, lots of buildings, lots of people, lots of things. And radio signals generally don't like that. So what they did is they did a comparison between FSK, you've heard me say FSK a million times today, right? An FSK counter radio and the LoRa radio. And what basically comes out of it is the LoRa radios went over 10 times the distance that an FSK radio could. This is actually, in my mind, rather poor performance from a LoRa radio. Now the packet error rate is what you're going to look at, this packet error rate percent. You know, we went all the way up to about 1/3 kilometers, right? And the FSK really died at 330. They got some unique reflections, kind of a cheat. That one that shows E, that was kind of a cheat. Remember I told you about multipath? Right? In this case, multipath worked in their favor, and things were bouncing off buildings, and they managed to hit like a sweet spot. So you can kind of throw out E for the FSK. They died at D, and LoRa went all the way out to somewhere between H and I, which is pretty good. There's no other radio technology that's going to get those sorts of performance out there. Doesn't mean that there won't be next year or the year after, but this is the way it is today. So now, that was all the LoRaWAN radio stuff. That was all the physical hardware stuff. On top of that, we have a LoRaWAN protocol. And the protocol starts talking about things like device types and different sorts of characteristics. The LoRaWAN protocol supports 3 different device types. They're labeled A, B, and C. Has nothing to do with the alphabet. It has all to do with how they're used. A just stands for all. All devices have this minimal functionality that they have to implement to be a LoRaWAN protocol device. What does that mean? The base functionality is that an endpoint will wake up and it will talk and send data whenever it feels like it. No synchronization with anybody else, gateway or any other endpoint. It wakes up, it talks, it sends it saying, it may wait for a response from the network, because this is a bidirectional protocol, and otherwise we'll go back to sleep. And the reason why we'll go back to sleep, the key thing is that the network cannot reach out to it. It's a lot like your cell phone, right? Actually, you can't just connect to your cell phone has to initiate the transaction. Similar thing for Class A. Then we have Class B. Class B implements the idea of a beacon. That's what B stands for. And this beacon is simply intended to give a few more times when the endpoint will wake up and listen to the network. So its primary purpose is to reduce the latency whenever the network wants to talk to an endpoint, right? Without using up too much power. The Class A, since the device is mostly asleep most of the time, it's using the minimal amount of battery power. B, you're awake a little bit more. You're not really transmitting, you're just awake a little bit more. So you're using a little more battery power, but for that, the network has far less effort or far less delay in talking to an endpoint when it needs to. And then you have Class C. Class C stands for continuous. It means continuously listening. So this is an endpoint that generally probably is not going to be battery powered unless it has solar charging capability or something else. It's going to need a more continuous source of power. But the endpoint acts just like an A. It will talk when it wants to talk, and it will listen for a response. But instead of going to sleep and being unavailable, it will go into receive mode and be sitting there waiting for the network to talk to it. So this is when you want to use a Class C, when you want a more responsive system, you want the lowest possible latency for the network to tell the device to do something. Usually that's when the device is controlling something like an actuator. Open the valve, close the valve, shut the nuclear reactor down, turn it back on, right? That's where you want to use a Class C device. And then in addition, the LoRaWAN takes the spectrum that's allocated to it, the ISM spectrum, in the different regions of the world and creates a thing called a channel plan. All the channel plan does is just say, look, I'm going to say that we have channel 1, 2, 3, 4, 5, and that means this frequency and this bandwidth, right? Now the data rate is controlled separately. So in the United States, we have a channel plan because we have 902 to 928 megahertz, which is a nice hefty chunk compared to the rest of the world. We can break that down into 64, 125 kilohertz channels up. Plus we've defined 8 500 kilohertz channels up, and then we have 8 500 kilohertz channels down. And the reason why we do that, we don't have any 125 kilohertz channels down, is your downlink is a precious resource in the LoRa world. So you want to be able to get as much through it as possible. 125 kilohertz downlink channel is just not going to have the data rate to allow you to service a lot of endpoints. Now remember, you're going to have a gateway that might be talking to thousands and thousands of endpoints, many of whom might be talking all at once. So you want a lot of uplink channels, right? For each one of these channels, you can have multiple endpoints talking using them depending upon the data rate or the spreading factor that they use, right? So 64 times, I think in the US we can use four different data rates, maybe 5. Okay, so let's just say 4. So at any given time, you can have 256 endpoints talking up to the network without interfering with each other using the 64 uplink channels. But then your network needs to answer, right? So how do you answer that many? So you use a higher data rate so you can get them done real quick. That's why we do that. So this is the US channel plan. In addition to that, the LoRaWAN defines a structure of the data, so you can know what the data looks like. In most of the time we use a thing called normal mode. It just says, hey, the preamble, remember I told you it sends out this thing that you're listening for, you can then lock on, right? That's the preamble. And then you have a header, a payload, and a CRC. And then inside that, there's further definition with different sorts of encryptions and things like that. There's also another way of using the LoRa radio is with a thing called implicit header, and that's that spreading factor 6 that I told you we don't use. So in the LoRa WAN world, there is no implicit header stuff, so you can ignore that. So the security architecture. This is a very generic slide because there's been a lot of change going on in the security architecture of LoRa. But LoRa is actually one of the most secure, LoRaWAN especially, one of the most secure protocols out there. There is, when you talk security in LoRa, you have to start with keys. All the encryption done in LoRa is AES 128-bit encryption. Now, an endpoint, when it's born, and it leaves, say, our factory, we give it a unique ID. It's called an EUID. It's a 64-bit worldwide unique ID. We've been allocated from a standards body or a controlling body that gave us a block. And it's unique. And then in addition to that, there are 2 keys that are put inside this device. And they're called root keys. In other words, they are the lowest possible level of key you can get. One is for the network, one is for applications. But you never really actually use those root keys to encrypt anything. They're used to derive other keys. So when an endpoint goes to join a network, the endpoint will go through this join process and it will talk to this thing called a join server that I mentioned earlier. There's a little bit of out-of-band communication between a device manufacturer and a join server owner, where when we create the endpoint, we share the root keys and the device ID with the join server. Okay? Now, when the device later on at some point goes to join, it talks to the join server. The join says, yeah, I'll let you on. And then the join server, I said, remember, generates keys. These are things called session keys. So that for that communication session, you have individually and uniquely generated keys. The endpoint never shares, and a network never shares a key over the air. What happens is when an endpoint goes to join, it says, hey, here's my ID, and here's a random value. And the join server takes that ID, knows what the root keys are, uses the random value, and generates, using an algorithm, some session keys, an application session key and a network session key. And the endpoint does the same thing simultaneously inside. And then the join server shares the network session key with the network server, and it shares the application session key with the application server, and then bows out. It's done. At that point, the endpoint now starts encrypting its network packets using the network session key. And the network server, having its own version of that key, knows how to decrypt it and can process it, and those two can talk. When the endpoint decides it's sending application data, it encrypts it using the application key. And the network server, when it gets that packet, says, I have the slightest idea what's in this. I can't decrypt it, but I'm going to pass it to the application dispatch server. And it's the application dispatch server that will then decrypt that application packet, take the data out, and then give it to the application that is expecting it. So in a very small nutshell, that's how security works in LoRa. There are some refinements that we're coming out with in LoRaWAN version 1.1. We are breaking up the message integrity code, which today is used with a network session key. We're actually breaking that into 2 pieces. We're creating a network session up key and a network session down key. And the 2 halves of that, each one is encrypted with the separate key. The endpoint has both the network session up key and the network session down key. But on the network side, in order to support roaming, okay, we have to break that up and down apart because of trust or not between a what we call an anchor or a home network server
and a servicing network server. So you get into this relatively complicated thing. I really need a whiteboard to explain it, but you have this network server, but there's several different kinds of them. There's a forwarding network server, which is just saying, I got a packet from this guy and I'm forwarding him on to another network server who knows what to do with it. That allows you to do a thing called passive roaming. I'm an endpoint, I'm in carrier A's locale, I'm moving around and I wander into carrier B, and A and B like each other, so they agree to roam, and so carrier B's stuff just starts forwarding it back to carrier A. That's called passive roaming. But then we have a thing called active roaming, which is, wow, I've completely left carrier A's world and I'm going into carrier B, and carrier B needs to control my channel. That has to do automatic data rate, some of this other stuff, right? So they need to have the ability to do that. That's the network key. So then the keys will get shared. And you then have an endpoint that's talking to a servicing network server. And the servicing network server will pass and will manage the network, but will pass the data back to the home or anchor network server. It really needs to be drawn up. And this is just being finalized now in the technical committee, so I don't have a slide for it. But rest assured that there's a lot of background stuff that's going on with security and the use of keys. We actually have a whole key hierarchy. And these keys, there's one other quick thing I'll mention about keys. This would all not be very good if these keys stayed alive or stayed in use for long periods of time. So the original, like today's LoRa network until 1.1 comes out, you do a join, you could go years without rejoining the network. That means your key would be the same because it's a session-based key. So in 1.1, there's a new concept called a rejoin. And it's going to be up to the operator and up to the endpoint, but the recommended frequency is once a week. The endpoint will execute what's called a rejoin. And the rejoin will cause rekeying all up and down the stack. So you get fresh keys, so that nefarious individuals will find it that much more difficult to decrypt your data. So all that is coming out with 1.1. And yeah, security is a very confusing topic. So let's talk about the LoRa Alliance. This is simple. The LoRa Alliance was put together to form an ecosystem. When the LoRa world looked at Zigbee, and they looked at Sigfox, they looked at Ingenue, these other kinds of networks, they said, well, what's missing? And what was missing is the fact that we didn't want to be a sole source system. Ingenue, Sigfox, there's one Sigfox, there's one Ingenue. You want to use their stuff, you have to do business with them. With LoRa, it's different. It's an ecosystem of companies. And with the Alliance decided that its primary function is going to be to keep us all working together. That's what it all boils down to. So part of that responsibility is to define, maintain, and manage a protocol specification, right? To figure out some way of guaranteeing interoperability so we don't run into the Zigbee issues, which any of you who tried to manage a Zigbee network before should understand it quite fully. And to have the standard be open so that it can be not only used across an ecosystem, but it can be adapted readily to vertical markets and needs, right, while still maintaining compatibility with other companies. So what has it done? The LoRa Alliance has 4 main committees. There's a strategy committee. They are looking out at more strategic sorts of implementation capabilities like localization, roaming, right? They're looking at feature level things like firmware updates over the air, things like that. And they feed into the technical committee, the technology committee, which takes that guidance and implements what it needs to in the protocol to support that. So that the developers and the manufacturers know how to make these things work. And then you have a certification committee which comes in and will allow a formalized certification process to be done on endpoints so that you can be sure that any endpoint will work with any gateway and any network. Now, if we don't have that, roaming's awful hard, right? Going from network to network. Now, we have the marketing committee. I really don't know what they do. I'm sure it's important. But actually, no, they are the face of the LoRa Alliance to the world. And they try and explain all the confusing things that I've talked about so far to the world in such a way that makes them like LoRa. So here's a couple real-world applications. This was in the oil and gas industry. One of the big things in the oil and gas industry is worker safety, right? You know, people can fall down, no one knows where they are, right? So having LoRa-based devices that can just simply tell you if someone's heart beating, right? Using localization to say where were they last seen, right? I mean, some of these things, very important because they are operating. This is one of those rare cases where the people are in the harsh environment. It's not too common, right? Normally, it's you know, we try to stay out of these things. But in oil and gas, they're in a harsh environment. But also you have site management. You know, such things as wall stresses on containers so that they don't fail catastrophically and cause major problems. Wasn't there a thing a few years ago where a whole oil facility blew up in Texas, I think it was? A lot of people were hurt from that. So having site management, it's more than just saying, is the tank empty or full? Is that tank going to cause something catastrophic too? In addition to that, your materials tracking. You go to a lot of these things, oil and gas, this is a prime example here, of where is my propane? Where is my, you know, oil? Where, you know, is it moving around? Is it in a truck? Is it in a tank? That sort of thing. So there's a lot of things that are enabled by LoRa. And then these are some very much specific ones. Meter reading, leak detection, things like that. One of the big uses of LoRa, by the way, is in fluid leak detection. You may not realize, but something like 25, 30% of all the water in the United States gets lost to leaks. And then the part that doesn't get lost, 80% is used by agriculture. And then we use, if I recall correctly, for all our showers and things like that, we use like 8% of the water. So we lose 4 times as much water to leaks as we all use in our day-to-day lives every year. And LoRa is really big in leak detection. It's one of my favorite topics, as you can probably tell. But, you know, emergency alert, flow monitoring, these kinds of things. LoRa is just very good in these kinds of environments where there's a lot of metal, there's a lot of obstructions, there's a lot of interference, and you need to get a signal through reliably. And that's it. Time for questions.
Thank you.